Hi kids, this video is on systems and conservation of mass. If you've poked around the website, you probably noticed that most of the units throughout the entire year start with this word conservation. If you're not familiar with it, the word conservation means to keep the same amount of. Maybe you've heard of people talking about conserving the environment. The idea there being that, this world is the only world we're ever going to get, and if we destroy it, well, we aren't getting another one. Well, conservation means the same thing. It means that however much you have of something is all you're ever going to have. And, if you talk to me in 5 minutes, I'm going to have the same amount. If you talk to me in 2 years, I'm still going to have the same amount. Any moment in any time that you could choose, you're going to have the same amount of something. In this case, that something that we're going to talk about is mass. But as we move through the year, we'll be talking about charge and momentum and energy and some other things that are conserved as well. The reason why they're the big units is because I think they're actually the most important idea in physics. These are a few of the unbreakable laws that physics have to do with conservation. Physics is fundamentally the study of the world and the way the world around us works. Of course, the world is a pretty complicated object, so to understand it better, we need to start by understanding individual objects better. And in order to separate individual objects from everything else that's going on around them, we will define those objects inside systems. So a system is basically a way of separating an object from everything else that's trying to touch it and interact with it. The way we show that an object is in a system is by drawing a box around it. So let's say we're interested in studying this orange box, which is not very interesting, but oh well. We're going to draw a box around that box, and we will call that our system. In this class, hopefully we'll be studying more interesting objects than boxes, like, for example, this Bugatti Veyron. I don't know if you're into cars, but if you are, you know this is the fastest production vehicle you can buy. Also will cost you about a couple $1,000,000 if you've got that laying around. At any rate, the Veyron is more complicated than that box. It has lots of parts. It has steering wheels, and it has headlights, and a big old engine. But we don't want to separate those parts from each other and analyze them individually. We want to include them all together in the Veyron. So the entire Veyron is going to go into my system. Now, a couple things to note. While all the parts of the car are inside the system, there's lots of things that are not, that are still interacting with the car. There's no driver in that system. There's no road or wind, lots of other things that might be relevant down the road, but probably are more complicated physics than we're going to be dealing with right now. The other thing is that you'll notice this is a dashed box instead of a solid box. Don't worry about that just yet. We're going to be talking about that in future slides. There are two types of systems that we're going to be talking about in class: open systems and closed systems. Open systems are the ones that have the dashed lines around them, like the Bugatti from the last page, and closed systems will have solid lines. The reason we have a dashed line around an open system is because in this kind of system, we mostly want to focus on the object in the system, but we realize that there may be some other objects that are actually interacting with this object as well. In this case, the object that I've chosen is a piece of Hi-Chew candy. I don't know how many of you guys have had Hi-Chew, but I find it fantastically delicious. We'll have some in class this year, I'm sure. This particular one is mango flavored. I probably got it at Costco. And I'm trying to separate that Hi-Chew from the world, so I'm going to make it into a system. But I realize that Hi-Chew isn't the only thing. There are other things that are interacting with the Hi-Chew that I at least want to be aware of. So I'm putting an open system around it because I want to think about considering the other objects that may be touching it or interacting with it. For example, there's a table, right? That Hi-Chew is being held up by something. If there was no table, it would be falling through the air. So because you can see that Hi-Chew is sitting happily on a table, even if I'm not putting the table in the system, I at least want to be aware that that table may be interacting with this Hi-Chew, so I'm going to leave dashed lines around it. Speaking of things that are interacting with it, obviously the Earth is also having an impact on the Hi-Chew. This may not be quite as obvious, but that Hi-Chew wants to fall down, right? Any object that you let go wants to fall down, and the reason is because the Earth is pulling down on other objects. It's pulling them together with a force of gravity. So the Earth is outside this system, but still might be having an impact on the object inside. If I'm being honest here, there's one other object that probably should be in the system. That's me, because Hi-Chews really don't last very long. Usually I eat them up. A closed system is a system in which the object is completely isolated from its environment. That means nothing else is touching it or acting on it. So if I wanted to take this Haichu and make this system more complete so I could close it, well, I have to think about everything that's interacting with the Haichu and include that in the system. So I could put the table also in the system. Now we're getting closer to a closed system because I know those two things are touching each other, so let's go ahead and put them both in the system. The system's getting a little bit bigger. But as we talked about in the last slide, the entire Earth is actually interacting with that Haichu too, so I have to stick that in the system as well. You may think we're done here. If I've got a system that includes the Earth and the table, what else is there that's going to matter to that Haichu? I'm, of course, included in the Earth. But it turns out that the entire Earth is actually being acted on by the sun and the other planets in our solar system. The Earth isn't just its own isolated system. So if I want to be honest, to make my true closed system, I got to include the entire solar system. You can keep backing out until finally you get to the entire universe, which is, this is a radio signal map or a microwave map actually, of our entire universe and all the mass that exists in the entire universe. And that's really the only closed system that we can really define, because everything else is being interacted on by things around it. So there aren't really very many truly closed systems in our discussions. The only one that is truly closed is the entire universe. So most systems that we're dealing with will be open to some extent. We realize that there aren't really ways of isolating things completely, but we can do our best. The big idea that this has all been leading up to is called conservation of mass. And what the law of conservation of mass states is that at any two moments in time, the total mass of a closed system is constant or conserved. Now, we're probably not going to be able to make any truly closed systems because we can't deal with the whole universe here, but we can approximate a closed system if we aren't going to let any mass come or go out of that system. So let's start with a before system right now that includes me and a Haichu that's sitting on the table. So this is the before system. And what I want to do is I want to look at the masses of all the objects in my system. So right now my mass is give or take 65 kilograms, and the Haichu has a mass of 0.0025 kilograms, which means that the system has a total mass of 65.0025 kilograms. So this law, conservation of mass, says that those two masses combined, the total mass of the system is always going to be constant. So at any moment in the future, we're going to have the same mass. Now, if you come back and talk to me in a few minutes, right, the total mass of the system is still 65.0025 kilograms, and I'm still in the system, but now all you see is a wrapper from that Haichu in the system. If you pick up that wrapper and you weigh it, you'll discover it has a mass of 0.0005 kilograms. So it doesn't take a rocket scientist here to figure out what happened. I ate the Haichu, and the mass of the Haichu still has to exist, though. It's still inside the system. So it's no longer in the wrapper, but that Haichu is now in Miss Nichols, which means that my mass has changed. Okay, the law of conservation of mass says the total mass is constant. So if the Haichu has been consumed, you can get out your calculator here. I'll give you a second if you want to, or you can do it in your head. You'll discover that the new mass of Miss Nichols is 65.002 kilograms. Give yourself a pat in the back if you were able to do that on your own. One thing you may not have realized, of course, is that despite the fact that I love Haichu, I'm actually allergic to mangoes, and it's probably going to make my face swell up and my lips swell shut, but it's worth it. Quick summary of what we've covered in this video. It's important whenever we're interested in studying an object or learning more about an object to define the system that it's in. In order to define that system, you think about which objects are impacting that system and whether or not it is open or closed. And then, of course, this big important law of physics is that mass is conserved in any closed system. So if you know all the mass in the system at one moment in time, you should be able to figure out the mass of the objects at any other moment in time.